In this video, we're going to talk through some of the fundamental underlying assumptions of statistical reasoning in psychological science. This, in particular, this discussion of p-values, is one of the more logically complicated things that we're going to talk about in the class. I'm going to do my best to explain it here. What I'd like you to understand at the end of this video is what a p-value can tell us, how to interpret those p-values, and what saying something is statistically significant actually means. So let's first talk a little bit about what it means when we're doing a study in general. What I'd like to do is use the example that we had in the previous skill where I talked about taking people outside of a church or outside of a civic building and comparing their attitudes towards different outgroups. So let's say that I'm interested in how people standing outside a church might rate Muslims. One thing that I could do is that I could sample everybody in the world, right? I could take all 7 billion people and put them out in front of a church and ask them about their attitudes towards Muslims. And as a result, I would end up with an accurate estimate of the response, of the mean, of the population mean, for attitudes towards Muslims outside of a church. And maybe that's 8. I don't know. But we know that not everyone in that population selected 8. Instead, that estimate represents a rather large distribution of scores that might range from 10 to 2, but that the average is 8. Now, if I had the ability to sample everybody in a population, I wouldn't need statistics. I could just take all 7 billion people in the world, put them in front of a church, and then take all 7 billion people and put them in front of a civic building, and directly compare the differences. But I'm actually not able to do that. Instead, what I have to do is take a sample, a subset of the population that is smaller than the whole, and make some assumptions about how well that sample represents the whole population. So what I'm actually doing is taking this huge distribution here and taking out some sample, some group. So maybe this section right here I might take out, or maybe it's this section. I don't actually know which section of this population I've taken out, but I do know that I have a sample. So now that I've sampled, say, 100 people out of these 7 billion, I have constructed my own sampling distribution. I've got my own mean, and in this case, just like we looked at in the previous demonstration, the mean is around 5.8 for people outside a church thinking about attitudes towards Muslims. That mean came from a population, the whole 7 billion people that it could have come from. This sample represents some segment of that population. The interesting question for psychological statistics is when I have 2 of these sampling distributions. So here I have the distribution for people outside of a church, but what if I also had another distribution? And this distribution is of people outside a civic building, and I find that that mean is somewhere around 7.2. The question then becomes, are these means, the mean of 7.2 and the mean of 5.8, different enough for us to say that they came from different populations? In other words, does this represent a different group than this, or did I, by accident, take 2 samples from the same population whose actual population mean is somewhere in between, and this just represents normal variation within the population? In other words, is the difference between the groups attributable to their positioning outside a religious structure or a non-religious structure, or are the differences attributable to random variation between 2 different groups of 100 different people? The statistics that we looked at previously, the t-test and the f-test, help us understand how different these groups are relative to the size of their sample. Let me give you another demonstration that I hope will make this more clear. Let's say that I have 2 very large jars of red and blue marbles. and they're all mixed together in these two jars. And my question is, does jar B have more red marbles than jar A? Now, I could conceivably take out all of the marbles, count up the proportion of red marbles, and say, yes, jar B has 10,001 red marbles, where jar A has 9,992, right? And I could do the whole population, but most of the time, what I would do instead is take a sample of those marbles. So let's say I had these two jars with 10,000 marbles apiece, and I want to know, is the ratio of blue marbles and red marbles the same or different across those two jars? Are these groups reliably different from one another? I could start by taking a sample of just 100 marbles from each group. Now, 100 marbles out of 10,000 is not a particularly accurate sample, right? I would have a lot of variability. That is, that sample could have come from anywhere in the population distribution. The larger my sample size, the more accurate my estimate of the true population mean. You can think about that in relation to the marbles. If I draw a sample of 100 marbles and compute the proportion of blue to red, that estimate is going to be more reliable the more marbles I take out of the 10,000 marble jar. A 100 marble estimate is going to be less accurate than a 9,000 marble estimate, right? The more marbles I have in my sample, the more reliable my estimate is. Now, I could take a sample of 100 marbles from both jars, and what I might find is that jar B has 5 more red marbles in their sample of 100 than jar A. Now, the question is, does that mean that jar B has more red marbles in it, or just that this sample happened to include more red marbles? A t-test will help us figure that out, and will tell us the probability involved. A p-value answers this critically important question. This is probably the hardest point to understand in the video, so I want to make sure you get it. The p-value asks, what is the probability that I would observe a bigger difference between my samples than I did observe if the real difference between the populations is actually 0? Let me put that in the context of the blue and red marble study. A p-value will tell you what is the probability of observing a difference between sample from marble jar A and sample from marble jar B that is bigger than the difference I did observe. Remember that I found there were 5 more red marbles in my sample from jar B. So a p-value tells you, what's the probability of observing a bigger difference between your samples, a difference bigger than 5, if the real difference between jar A and jar B is 0? Let me phrase it one more way. If jar A and B have exactly the same ratio of red marbles to blue marbles, what's the probability that I would have drawn this 5 different sample if they really come from the same jar? That's what a p-value tells you. If that probability is very high, that is, it's very likely that I would observe this much difference or even more difference if they really weren't different from each other, then I know that my sample difference isn't a reliable estimate, that 5 marble difference really doesn't tell me anything. However, if I had a really low probability, that the probability of observing more than 5 marbles different in a very large sample was very low, then what that would mean was that my difference is reliable, and that I can say that jar B does tend to have more red marbles than jar A. So let me put this back in the context of our previous study. Let's say, for example, that I have sampled my individuals standing outside a church, and I find a sampling distribution with the mean down here. I also sampled people outside a civic building, and I find a sampling distribution with the mean up here. So I can say these groups are different from each other, but are these groups reliably different from each other? Do these 100 people outside a church and outside a civic building have a big enough difference between them that I can say these come from different populations? They're reliably different. If I took another 100 people and sampled them outside a church and a civic building, I would find similar differences between them. Or is it more likely that instead I'm actually sampling from the same population that these are actually from the same distribution, and I've just accidentally gotten some people who are more prejudiced towards Muslims in this Christian context, and some people who are less prejudiced towards Muslims in the civic context, but they're actually members of the same group. They aren't really reliably different from each other. A p-value tells you the probability that you would observe this difference, the one we observed in that study, if they actually come from the same population. So what's the probability that I would see a 5.8 relative to a 7.2 if they really weren't different from each other at all? If I measured everybody and they really weren't different. That probability, p, is something that we're really interested in understanding. So let me give you a few examples of p-values. If p is less than 0.05, what that means is that the probability of observing a difference that is at least as big as the difference you observed, if the real difference between groups is 0, is less than 5%. So less than 5% of the time, you would expect to observe a difference bigger than the one you observed if the true population mean was actually the same across the two groups. If less than 5% of the time you would expect that, then you can be reasonably assured that this is a real difference, that the difference between the groups is reliable, and that we would expect to see that difference given the same sample size with a different group of people. Psychologists talk about the critical point of this probability being p equal to 0.05. That means there's only a 5% chance that you would observe a bigger difference if the real population means were actually the same. So what that means is that if p is less than 0.05, we call that statistically significant. That means this finding is statistically significant, and we can say that reliably we would expect this difference between groups. It's worth noting that in this video we've talked about p-values as it relates to mean differences, but you also have p-values as they relate to correlation coefficients. A correlation coefficient's p-value tells you the probability of observing a stronger correlation than the one you observed if the real correlation between those variables is actually 0. So what's the probability that I would have accidentally observed this very strong correlation, given this sample size, if the real correlation in the population among all people is actually 0? So let's say I observe a correlation between height and IQ of 0.2, positive 0.2, meaning that as height goes up, IQ goes up, in a small way. So given my sample size of 100, for example, I would say, what's the probability that I would observe a stronger correlation between height and IQ than 0.2 if, in reality, those two variables were completely unrelated to each other? I might find the probability is very high, say 0.5 instead of 0.05. That means there's a 50% chance that given my 100 people, I would observe a correlation of 0.2 or higher between height and IQ just by accident, because I don't have very accurate estimates of height or IQ. As a result, my observed association in this sample of 0.2 is not reliable, and I wouldn't say there's an association between height and IQ because that statistical association is not reliable. My p-value tells me that if I were to do this study again, I might observe a more drastic association between them or a much less drastic association between them, because my probability of getting a very different value is very high. P is greater than 0.05, and that means that value is not statistically significant, and what that means is that those values are not reliable. Let me show you again what this looks like in a particular journal article. So you've already seen this table, but now you should be able to interpret it more clearly. Instead of just looking at these mean values, we actually have an estimate for how reliable the differences between those values are. As the F statistic increases in size, and this is the same for a T statistic, the probability of observing the difference that makes that F statistic appear, if the true population means are actually the same, decreases. So you can see here with this Mondo F statistic of 15.98, the p-values are listed below. P is less than 0.001. What that means is that less than 1% of the time, I would expect to observe a difference this big between two samples of the same size if they came from the same population. So I can be reasonably assured to say these don't come from the same population. These two groups are reliably different from each other. The religious group is reliably lower than the control condition when it comes to attitudes about Africans. We can see the same thing with any of these variables. These asterisks tell you the level of probability. So here, for example, among attitudes towards the rich, we do see a difference, but that probability value, p, is less than 0.05. So that means only 5% of the time would I expect to observe this difference between 6.35 and 7.40 if the real difference between these two conditions in the population was actually 0. So my sample of 100 people or so in each condition produced this difference. What's the probability that they actually came from the same population instead of from two different populations? Really, it's less than 0.05, less than 5%. Whereas the population here is less than 1% likely to be the same population. What about for Christians? I mentioned this in the previous video, that the difference between attitudes towards Christians in the religious and control context is very small. I have a mean of 6.62 and a mean of 7.27. What's the probability that I would observe a difference greater than this difference if the actual population means were right on top of each other? That is, they were the same. Well, as you can see, the probability is greater than 0.05. That means that more than 5% of the time, I would expect to observe a difference at least this big, even if the population means were exactly the same. What that means is that there's no reliable difference between attitudes towards Christians in the religious and control contexts. Although I have observed this difference, the difference isn't big enough, given my sample size, to say, yep, I would observe that if I took another sample of 100 people and compared them with each other. P-values are critical to understanding results sections in articles. They tell you whether or not the statistical differences or associations that the authors are reporting are reliable and likely to be repeated. What you should look for in results sections is whether or not these analyses are statistically significant. That is, do the F values or T values or R values in the case of correlations indicate that we would observe the same difference or the same association if we ran the study again? If so, that p-value will be less than 0.05 and we will term it statistically significant.